All right, hey Amy. Help you out here with these problems that you requested. Starting off with number 4. So you're given a table that gives the time in minutes as the x value, and the y value is cubic feet per minute. And we're supposed to approximate the total cubic feet. Well, recall if I'm finding the area under this function, whatever it looks like, my units are going to be minutes times cubic feet per minute, and those cancel, so it's cubic feet. So we definitely want the area under this function. Now I don't give you what the function is, I give you a table. So that's where we're going to use Simpson's to approximate it. We want to find the volume by taking the integral from 0 to 10 of f of x dx. So think about what's your change of x. While looking at the table, we're given every minute, so your change of x is 1. And then you have the different y values to go along with it, right? So we have what? Change of x over 3 times, then what do? Well, we do the first y value looking at the table, it's 5. And then we do 4 times the second y value, which is 4. And then 2 times an xy value, which is 4, and continue that on to approximate that volume. So there's help with number 4. Okay. Let's go to number 6. And I think looking at number 6 here, the integral from negative infinity to infinity of x over x to the fourth plus 9 dx, first probably should take a look at the graph. And I have it graphed right here in red. Okay. Now, one thing that we probably notice right away when we look at this graph is it looks like it's an odd function. Looks like it's symmetrical about the origin. So I wonder if these are going to cancel out and give me 0. Well, the first thing we have to figure out is, do they converge? Right? And I think it would make sense to split this from 0 to infinity and see if that converges. And if it does, what does it converge to? And then 0 to negative infinity. So as I showed you from here, let's split it into the 2 and then work on each of these as improper integrals, right? So the limit as t goes to negative infinity of t to 0. And then the limit as t goes to infinity of the integral from 0 to t of x over x to the fourth plus 9 dx. So do each of those individually. Now, if you need help in actually finding the antiderivative of this, I've given you a little bit of work over here. If we let u equal x squared, okay, and I follow that substitution, du dx equals 2x, dx equals du over 2x, we'll notice that x to the fourth is x squared squared, which is the reason I picked u to be x squared, because now I have x over u squared plus 9. Then these x's end up canceling. I bring that 1/2 out in front, and I have something here that looks a lot better. In fact, it actually looks a lot like the derivative of the arctangent, if only this were a 1 instead of a 9. So what I would actually do is I would go back and I would say, you know what, let's let 3u be equal to x squared. And the reason that I would do that is we have x to the fourth, which is x squared squared. And if I let x squared be 3u, I have 3u squared, which is 9u squared. So that puts a 9 right here, and that allows me to factor out, so this is going to be a 1, factor out the 9 from the denominator, and that's now an 18. So see if that helps you for number 6. Got one more to go here in number 14, and let's go back to Desmos. So we have a function that's bounded by x to the 1/3, which is in blue, and x squared, which is in green, and we're rotating it around the x-axis. All right, so we got to take this region right in here and rotate it around the x-axis. So that's what I have drawn. Okay. So how do we do that? Well, we use cylinders to help us with volume, right? So what we could do is we could say, all right, well, if I take and I rotate this rectangle around, I'm going to get a cylinder that looks something like this. Okay. However, we have a problem with that because we don't want this part. So what we do is we have to take another cylinder like this and rotate that around, and what that's going to do is that's going to set up like a washer-like effect. And it's going to cut out that inside. So what we really have is we have an outside radius and an inner radius. So what we can do is we can say, all right, the volume is going to be the integral from 0 to, well, we need to know what this x value is. Okay, and I didn't tell you what it was in the problem, but keep in mind what these two functions are. We're looking for where they intersect. I'll let you figure out what this is. Okay. Now remember, it's pi r squared dx, right? Because the height of these is dx, right? This is our volume formula for a cylinder. But now our outside radius is going to be x to the 1/3. So we have x to the 1/3 squared dx. So that would give you the volume of the big cylinder here that I have in green. That whole thing. But then we have to subtract off the volume of the inside, 0, 2. You're figuring out what that is. Pi, now the inside radius is x squared. So you have pi r squared, so pi x squared squared dx to subtract off the volume from this inside radius. Okay? So, gave you quite a bit of the setup on that one. We just have to subtract a smaller cylinder from a larger cylinder there to find that volume. Get a pretty neat looking object when you do that. So, I hope that helps. Let me know, and we'll talk to you later.